One important part of uncertainty quantification will be inverse modeling. And so we'll cover in the next 4 sessions various approaches for inverse modeling. This first session, I will talk about deterministic inversion. So here we look at the material in the book in chapter 6 called Geological Priors and Inversion. So the overview of these inverse methods are first deterministic inversion, where we try to get one smooth solution. Then stochastic inversion, where we realize that, of course, that smooth solution is not quite as useful as we think for uncertainty quantification. We like to get many solutions that quantify uncertainty due to the ill-posedness of the problem. Then we'll look at methods that try to avoid the complex model inversions and look at a method called direct forecasting. And then finally, also look at importance sampling. What if we need to do this inversion many times in time? For example, I acquire new data, so how can I do then this inversion quicker? This will be importance sampling or sequential importance resampling, particle filtering. They're all sort of the same names or the different names for the same idea. Let's revisit our electrical resistivity tomography case. Remember that we are injecting heat in the subsurface and try to detect the temperature increase or decrease, which is useful for designing shallow geothermal systems. So electrical resistivity tomography is such a method, and particularly time-lapse electrical sensitivity method. Resistivity tomography is a method being used to image the temperature anomaly to imaging the electrical resistivity distribution in the subsurface. So electrical resistivity tomography, therefore, depends on a number of things. The electrical resistivity depends on the clay mineral content in the subsurface, the water and salinity, the porosity, and the temperature. So the way the problem, therefore, is set up, because we really are mostly interested in temperature and not so much in the other ones, is that we'll inject electrical currents by means of current electrodes and then measure the potential by means of potential electrodes. And so thereby, using some kind of a geometry of configuration, we can then, using Ohm's law, just simply extract electrical resistivity. So this electrical resistance or apparent resistance that we then measure at the electrodes, the potential electrodes, can then be inverted into an electrical resistivity distribution. So if we do then a time-lapse resistivity, then basically everything remains relatively constant. So we're not changing mineral content, water saturation, or porosity, and so therefore the time-lapse will mostly pick up this temperature. The idea of deterministic inversion is because, of course, there are many solutions, many Earth models that will match this, the observations that we obtained through these experiments, is to then turn this ill-posed problem, the many-solution problem, into a well-posed problem, and therefore obtaining only one solution. And for example, here we see one such solution obtained with a method. And so what we'll cover now is essentially how we can obtain such a deterministic and smooth inverse solution. So that's just one particular form of geophysical measurements. There are many forms of geophysical measurements. Each use a different, say, physical idea or physical method to sense what's in the subsurface. So these geophysical methods are listed. Some of these geophysical methods are listed over here. For example, methods such as seismic, magnetic, gravity, ground penetrating radar, the one we just saw, resistivity, also self-potential, and then any time-lapse version of these methods. That means repeating these methods over time. So what geophysics attempt to do is to measure a geophysical variable. For example, with seismic, we can measure elastic modulus or bulk modulus or density. With magnetic, we're going to measure magnetic susceptibility, etc. But of course, what you're really interested in is not the geophysical variable, which is the one we measure, but the physical variable that essentially defines this geophysical variable. So the physical variable that we're interested in, for example, in reservoir could be fissures or pore fluids. In the resistivity case, as we saw, we can look at water contact salinity, clay contact content, etc. So, and these have many applications. So the issue, of course, or the idea here is that we use a geophysical method that informs us of a geophysical variable, and the geophysical variable is going to inform us a physical variable. But these relations are all very uncertain. So a geophysical method will not perfectly inform the geophysical variable, and a geophysical variable, for many reasons, will not perfectly inform the physical variable. That's because our understanding between geophysical variable and physical variable may be limited for that particular case, and that's the topic of rock physics. To solve an inverse problem, we would just simply use the full Bayesian formulation. We'll simply say that we have some model parameterization. We state a prior uncertainty on that model, and then we specify a likelihood distribution, and from that we define the posterior distribution. And so the way we would approach then is to first do this various definition, define that distribution, these two distributions on the right hand side, these two here, which then defines distribution on the left hand side, and then we'd sample from that distribution. And so this is, all sounds very reasonable and easy, but in reality, of course, it's not. Because the question is, first of all, what is this prior distribution? And we've discussed this already in the context of this course. This prior distribution can be very complex. We can have many uncertainties in the model parameters, and we can generate many complex spatial realizations of those model parameters. So this distribution is essentially not very analytically certainly not known, and it's mostly accessible through Monte Carlo. The second problem consists in then specifying a likelihood distribution. A common misconception is that the likelihood distribution is a distribution that measures error or some measure of distance. And that's not necessarily true. The likelihood distribution is just another multivariate distribution that models the uncertain relationship between data and model, and that uncertain relationship can have many origins. It can have an origin related to we do not fully understand the physical model that relates the data and the model uncertainty, or there may be measurement error. We do not fully measure essentially what the observations are. We measure something else. And so this problem, while conceptually it seems very easy to write this down, to solve this problem actually in practice is very difficult. And so the way we're going to approach this is to first look at simplification of this formulation. So what we'll do is essentially we'll try to derive from this general formulation more limited formulations. For example, what if the forward model is linear? What if I have a Gaussian error distribution? And so on. And so and those become then very solvable problems. And so as we then progress through this sessions on inverse modeling, we'll start to increase the complexity of how of the kind of problems that we solve, and at the end we'll then revisit the full Bayesian formulation for actual real applications. So let's look at this likelihood distribution. So the previous slide, I mentioned how this likelihood distribution essentially is a full multivariate distribution. It should not be confused with an objective function. As you see in a bit, an objective function is a highly simplified formulation or situation that is derived from this full multivariate distribution. So the two main simplifications that we consider here is that we have a forward model. That means that there's a way to, given an Earth model M, to evaluate what the data response would be. And so this forward model has to be written in this functional form. Now this is, of course, the first problem. In many cases, we'll have to solve partial differential equations since we simply don't have this functional form. But we do assume here that given a true Earth, we'll get a true observation. And so that's one simplification. The way that we address some of these simplification is to deal with what's called error models. And so error models are simplifications of the full multivariate distribution. A data error model would simply be saying what is a model for the way errors occur while measuring. And a model error would simply state what is the simplifications that we make, for example, in either the specification of M or the specification of the forward model G. And so these are, of course, less accessible. Data error we see in a bit, we can try to estimate that by reciprocal measurements or repeating measurements, but model errors are basically conceptual errors that are very difficult to understand. One way that the model error often is included is by proxy models. For example, I can have a very complex forward modeling operator G, which is say a full physics simulation, although of course full physics has to be taken with a grain of salt because nothing is really full physics in the sense that we do not necessarily understand fully the physics. But imagine this full physics simulation happens and we replace that by some proxy simulation, then we're making a model error. in that sense. And so by doing some experiments, by running some full physics models and proxy models, we can understand what that error is, and that can then be included. But again, we have to be careful with saying this is a model error in the sense that our modeling is always a significant approximation of reality, and we will rarely know exactly how that approximation is working. So let's talk about data uncertainty. So what's the general idea here? So the general idea is that we do not actually observe the data variables. What we observe is something else. And so there has to be a formulation of this problem. And what typically, of course, is done is that we have a simple error model. We say that our observation is basically some data plus some error. So that error term is some error variance is being used, but that's only just one particular simple simplification of that. So how do you formulate this problem? So let's look at this graph here at the bottom. So what we do is we have our true Earth. We don't know that. We apply measurements. We want to measure something, for example, resistivity. And so if we had perfect measuring tools, then we will get some measurement. But because measurements are not perfect, there is setup, there is setup error, there is what we think is a geometry of the measurement, but in reality the geometry is different. Of course, there is noise that is coming into the question. There are many issues that are these measuring operations that doesn't have to be just random noise that lead us to getting the observation. So instead of getting this, which is what we'd like to have, our measurement operations only give us this. So basically, the data uncertainty is simply saying what is the conditional distribution given that this would be the actual measurement, the true measurement D given what is the actual measurements that I have given the true measurements. And so, of course, this distribution is not very well known and will require modeling again. First of all, you have to realize that this measurement error may be a function of the actual Earth, and that's what we show in the previous graph. And so that's quite logical in the sense that some Earths are easier to image or model to acquire data on than other Earths. So in signal analysis, this basically means that the noise is a function of the signal. And so because we don't know the signal perfectly, we also don't know this variation of noise perfectly. And so that requires then modeling it through some conditional distribution. The methods that you're probably more familiar with, which are limited formulations, is to assume an additive model, to say that all these measurements, errors, and these operations can be simplified through this error here, where we say that our observations are simply whatever that is actually the measurement plus some epsilon. And so therefore, then this conditional distribution simply becomes a distribution of the error, because this is now the distribution of this difference, which is the error that we make. And what's commonly done is to assume a Gaussian distribution where we can have some covariance of the errors. For example, we can say that errors can be correlated, or if error is not correlated, then we make this a diagonal matrix. And so that will be the most common idea that's being used. But do note that this common idea is not is essentially a limited formulation of a more broader idea of how we can represent data uncertainty. So now we'll deal with the specific situation where the forward model is a linear model, and that will be then called linear inversion. A linear inversion is simply saying that specifying here that our forward model G multiplied by M provides us with D. So now we don't have G of M, we have G, the matrix G times M, and so this matrix G is specified. So that means that our distributions are going to be highly simplified. So first of all, if you need Bayes' rule, what we do is we need to specify a prior distribution, and then we can specify a likelihood distribution. For example, a prior distribution on a model parameter, you could say, well, a priori, I know something about it. I know that the mean of my model parameters is some mean M prior, and that I have some kind of correlation between these parameters. For example, if you're in the spatial case and you're looking at spatial distribution of permeability, this could simply be the mean of your distribution of permeability, and the covariance could be your variogram of permeability. So then the likelihood model is a simple error model that is Gaussian. So we say that there's some error that exists between what I'd like to measure, D, and the actual observation. And we model that through a covariance of error. And that's basically what we saw in the previous slides. So now we have specified our prior model. We specified our likelihood distribution. And so we plug that into Bayes' rule, and we get our posterior distribution. So our posterior distribution now is again a Gaussian distribution. So that has simply to do with the fact that our prior distribution was Gaussian, our likelihood distribution was Gaussian, and our forward model is linear. So as a result, our posterior distribution is again a Gaussian distribution. So that's really nice. And so the first part here, we see the likelihood part, and the second part, we see the prior distribution part. So now we have essentially a posterior distribution that's Gaussian, so we can calculate the center of that distribution, which is the most probable solution. And so the way we do that is by maximizing or calculating the maximum of this. So after some derivation, you find that the maximum of this is simply the prior plus a correction term. So in other words, our mean, our most probable solution is our prior mean plus a whole correction term, and that correction is function of the error that we have from the beginning. So remember, this is the forward model applied to the prior mean. And these are our observation, and here we see that we have matrices that have to deal with our forward model G, our prior covariance on M, and prior covariance on D, which is our measurement error. So in that solution, we can also calculate what's called an accuracy. That means the covariance in that solution. And so that covariance is simply the prior covariance, and then again you have a subtraction which has to do with the forward model. So those who are already have taken courses in geostatistics will recognize that this looks a lot like the Kriging variance, and that's essentially what it is here. So that looks all very complicated, so let's make it much simpler. So we'll take in the previous slide the minus of the logarithm of the posterior distribution. The way why we do that is because, first of all, taking the logarithm, we'll get rid of the exponent. Taking the minus, get rid of the negative signs. And so then we also get rid of these covariance matrices simply by stating they are all equal to identity matrix. And so what we're left with is simply this very simple form, where we see, again, this has to do with our mismatch, and this has to do with the prior distribution. So what's often done is now we turn that into an objective function, and this is where the idea of objective function comes from. So you notice immediately that the idea of objective function is a very specific limited formulation of a Bayesian inverse problem, and we should never lose track of that. Often inverse problems are started by formulating objective functions, but objective functions are just one specific way of looking at that problem. And in fact, it's a very limited way of looking at an inverse problem. But nevertheless, we can formulate this objective function, which is saying that I have an objective function that consists of two parts. One part has to do with the difference between my observation and what I forward modeled, which is a linear function. And the second part has to do with how much I deviate from some initial guess that I have, which is this part. And so we can change this M prior into any kind of initial reference model or initial guess. So this can be solved in this linear case can be solved by least squares, and so the solution of that is then in this particular form here. So in this particular form now we see these various terms appearing. The alpha is called the regularization term, and it's something that we'll start discussing later on when we show a couple of examples of deterministic inverse problems. That's how we cover linear inversion. Now, for nonlinear inversion, there is actually a lot to say about this, and we're just not going to go into the great details because essentially the smooth nonlinear inversion is not what is going to be the main focus in uncertainty quantification. Something can be quite useful, but of course it doesn't provide you uncertainty quantification. So here we see a simple sort of conceptual representation of the various forms of inversion that we could run into, or situations that we can run into. So imagine for example, you're in the bottom line here, x-axis would be the model space and D would be the data space. And so if M was one-dimensional and D was one-dimensional, when you had a joint uncertainty between D and M that's Gaussian distributed, then basically the forward model is this regression line, or this linear model. And so by making the cut through this bivariate distribution, we get a univariate Gaussian distribution. So you can imagine this now for high dimensional problems exactly the same. If I have a high dimensional joint distribution between D and M, then if I make which is multivariate Gaussian, then if I take a slice through that distribution, I get again a Gaussian distribution, and I can calculate the mean and variance of that distribution, which is then the posterior mean and posterior variance under that linear case. So now we can go and extend this to the nonlinear case. In the nonlinear case, simply we don't have G as G of M, but G is G of M. And so then many situations can occur. First of all, we can assume, for example, that in the vicinity of the prior mean, that my forward model can be approximated with a linear model. For example, what I do is I take the prior mean, I look at the forward model there, and I calculate some kind of derivative of that model, which gives me the idea of a linear approximation of that nonlinear model. So I'm replacing essentially this nonlinear model with a linear model, and then I find again what slice through this distribution and find again the posterior distribution. Of course, then I have situations where that's not the case. I can look here, for example. Here I see that in the center of this distribution, my forward model is moving a lot, it's changing a lot, so I can make that approximation. So what we do is we try to find what's called the maximum likelihood point. So we try to find a point where essentially the forward model and the distribution intersect. So this is that maximum likelihood point that has to be found by some iterative method. Once I find that, I make the linear approximation and I calculate the posterior distribution. So this all works for these simple cases, but of course, when your forward function is let's say starts to misbehave, then I suddenly start to have two distributions. In other words, I can't make this linear Gaussian model doesn't apply anymore. And even worse, of course, when my joint distribution between D and M is not Gaussian, maybe even multimodal, then I get a very complex situation. And so these are situations that you can deal with within this simple deterministic inverse framework. So let's look at an example. Here is an example of the coast in Belgium, where we, like many regions in the world, we're dealing with saltwater intrusion due to, for example, pumping or over-pumping or the construction of inlets where saltwater can intrude in the subsurface and starts to interfere with the freshwater groundwater system, which is often used for either irrigation or for drinking water. And so in order to monitor that, people have essentially done an electrical resistivity measurement, taken those measurements. So here we have the area between France and Belgium, a water catchment area. So this, this is possibly a few kilometers long. And so here we look at this triangle, this rectangle, and we see that several lines of tomography have been taken. And so the question is, okay, given these measurements, can we measure the saltwater intrusion or map that? And so why electrical resistivity tomography? Well, saltwater, of course, changes considerably the resistivity in the subsurface compared to freshwater. And so that's something that will allow us to image that. So we'll do 3 examples of deterministic inversion. Remember, in deterministic inversion, we have a term here that has to do with our objective function, the difference between the observations and the forward model. So we are going to use a nonlinear model, not a nonlinear model. And then there's this regularization term. And so this regularization term is added, of course, to make sure that we get just one solution. But of course, we have many choices of regularization terms that we can add, and people have proposed many things to do that. And so we'll go over a few of those examples. So in the first example, we'll have essentially the difference between my observations and my forward model, and then we also have something related to measurement error. So this has the error variance of the measurements. And in geophysics, often, and particularly ERT, we can actually obtain some statistical information about that, because we can switch the current electrodes in potential electrodes and vice versa, and that gives us several measurements of the same thing, which allows us to then look at differences and allows us then to quantify some error variance. So that's the first part. And then the second part here, we added what is called a smoothness constraint. So we don't want our results in, if the idea is to get a smooth solution, is we don't want our final result to essentially look too rugged or too rough. And so what we can do is we can add a gradient operator to that model. So this is basically see is a difference operator, gradient operator. That means that if this gradient, if this product becomes big, then that's going to be penalized. And so what that does is it makes our solution look smooth. So when we solve that through nonlinear optimization methods, here iterative Gauss-Newton methods, then we get this kind of nice smooth looking constraint inversion. So another byproduct often of deterministic inversion is some kind of a sensitivity of the solution. And so in other words, where in the solution space do I get the most sensitivity? That means if I change those solutions, they'll have the biggest impact. And of course, for geophysical measurements, this insensitivity will increase with depth. That we have, this is a whole more sensitive area, or sorry, cumulative sensitivity, or more so, I should say, not sensitivity, a more uncertain area. And so the resolution drops in the depth as compared to the top. So this cumulative sensitivity is a way of representing the resolution of the geophysical imaging that is being done. Okay, so we can also have regularization by means of a reference model. For example, I could say I have some initial guess of some resistivity model, and one thing to do is simply take a homogeneous resistivity model, which can be calculated from a few wells. We can look at the mean resistivity, and we take that as our reference model. Or it could say, well, I know through boreholes that the subsurface consists of a few layers, and so I assign to each layer a resistivity that's different. So here that's done in this way, which is through a homogeneous reference model. So there I simply take a homogeneous model, and here we use a three-layer model. You can see probably this is the first layer, this is the second layer, and this is the third layer. And often this can be obtained from borehole information. Final method shown here for deterministic inversion is that using a spatial covariance. So spatial covariance means simply that we acknowledge that our electrical resistivity is a spatial variation. And so the spatial variation can be quantified through a variogram or spatial covariance. And so one way to inject that information is to add this term here on the right-hand side. And so let me get my point pointer. Here we have that term, and so here we have our covariance matrix. So this is essentially the variogram that is being used to construct that matrix. And so if we add that term, of course, then we can start playing around with this variogram. We can say how much anisotropy is in this variogram. For example, in the horizontal versus the vertical, do I see more horizontal continuity than vertical continuity, and how much is that exactly? So that information can be injected. And so here that is being shown here, for example, this is remember our smoothness-based inversion. So here we're imposing a spatial covariance model. And so then we start playing around with the range of that covariance model. So here we're looking at extending the range in the horizontal direction compared to this one. So we see that we get a solution that's flatter, or the range in the vertical. So we see a solution that's more continuous in depth. And so that allows me to add some additional information to the system. Here in this case, what they also did is they compared that with borehole information. And so you see that many of these inverse methods actually predict really well the resistivity that is being measured in the borehole. And that resistivity is measured through some type of well logging. Okay, I think these methods are really nice. They provide basically an insight into the geophysical data by providing a smooth solution. But of course, regardless of all the methods you use, whether you use a reference model or a structural inversion or some kind of spatial covariance in there, all the solutions still look equally smooth. And of course, in reality, resistivity or that property that you're trying to invert is not as smooth as the solutions provided. The other, of course, problem is that all solutions are deterministic. While some of these solutions also provide what's called the Hessian information in the solution, that means the second derivative in the solution, which is an idea confidence that you have in sensitivity, it's only a local sensitivity and a local confidence. It's not what we call a global sensitivity or a global confidence, which would be an uncertainty quantification. So again, don't confuse the so-called uncertainty provided by this deterministic solution as an actual uncertainty quantification. It's not. It's simply a sensitivity to the method in the solution space, in that particular solution, in the minimum of your objective function. It's not an uncertainty quantification. So what will come next is that we'll move away from this deterministic inversion, but use the same Bayesian formulation to specify methods for discuss methods for stochastic inversion.